This is the Friction Lab. In this lab, we will be measuring the frictional force of a wooden box with a mass in it as it is being pulled across the surface. So in this lab, we just need a box, a wooden box. We need a mass. This one is 500 grams. And you will need some spring scale. So I have two spring scales here. This one, the green one, goes up to 5 newtons. And this one, the brown one, goes up to 10 newtons. So the first thing we need to do is find the magnitude of the weight of the wooden box with the mass in it. Now remember, weight is the mass of the object multiplied by the strength of gravity, or that gravitational acceleration. So we're not going to calculate weight, we're just going to measure weight, and we can work backwards to find the mass. So I'm going to use this brown spring scale to pick up the box by the hook with the mass in it, so we can find the gravitational force, that weight of both the box and the mass. So I'll go ahead and put a zoomed in result of the weight of the box. Now remember, weight is a force. It is a vector quantity, and it is being pulled down. So we're just going to be talking about the magnitude of the weight. Because normally the downward direction would be negative. We don't want to use negatives in these calculations, but we do need to know that the direction of weight is pulling down. So using this equation, we can calculate the mass of the wooden box and the cylinder. Now for the variable lowercase g, that is the strength of gravity, right? That's like the gravitational acceleration. Now, like I said, the acceleration is always going to be in the downward direction. It is going to be a negative number. We're just going to use the magnitude, that positive value. So the actual value for the lowercase g is 9.81 meters per second squared. I know some people use 10 meters per second squared because the numbers are close enough and they just want to practice the math and not get lost in those decimal points. So now that we have found the weight of the box and the mass, we're going to pull them both across the table, and we're going to find the force that it takes in order to start the box sliding across the table and keep the box sliding across the table. Now for this experiment, what I'm going to do is I'm going to use that green spring scale. This one only goes up to 5 newtons. We probably won't need any more than that. If we do, we always have that brown spring scale with 10 newtons. So I'm going to go ahead and pull this box. So notice what happened there, right? I'm applying a force, right? That static friction is applying a force right back until there comes a point at which, well, I overcome static friction and now I'm sliding across the table. I'll go ahead and zoom in on this experiment so you can see what's happening to the spring scale and we can get that data. So I'm gonna pull, and then there's gonna be a point at which it starts to slide. Then I'm gonna pull the box across at a constant velocity. That's the key. We don't want it to accelerate, and we're gonna find out the force that's required in order to keep this box sliding at a constant velocity. So you've probably noticed it takes a larger force to start the box sliding across the table than it does to keep the box sliding at a constant velocity. So now that we know that the force required to start the box sliding and the force required to keep the box sliding at a constant velocity, we can make our friction graph. So this is what every friction graph should look like. So what happens is that static friction, if I'm applying a force, my applied force with the spring scale, I'm applying a force. Static friction is what's preventing it from sliding. So my static friction force is going to match my applied force, just in the opposite direction. Now in all of these, we're just going to be dealing with magnitude, not direction, so we don't have to deal with the negatives. So if I'm applying like 1 Newton, what's going to happen is, well, frictional force is applying with 1 Newton right back. And it keeps going until that point, until that maximum amount, that force required to overcome static friction, and then it starts to slide. It doesn't matter how hard I pull, once the box is sliding, kinetic friction can only provide so much. It doesn't matter how hard I pull, kinetic friction is always going to remain the same. So we can use the information gathered in the lab to make our own friction graph. So what I do is I look at that maximum amount of force required to overcome that static friction. That's going to be the point. Up until that point, I apply a force, static friction is going to apply the exact same force in the opposite direction. Now once I overcome static friction and it's sliding, it doesn't matter how hard I pull, these two surfaces under this condition can only provide so much of a kinetic friction. That's going to remain the same. It's always going to be the same kinetic frictional force as long as it's sliding. So let's take a look at the equations for friction. So there are two equations, one for static friction and one for kinetic friction. So let's take a look at the static friction first. Now when we're calculating static friction, remember, static friction always matches the applied force until it starts sliding. Now this equation, what it does is this is going to calculate the maximum force that you must apply to overcome static friction. It's basically that point in the friction graph. So when we were using that lab, if I was pulling with a force, right, that moment just before it starts sliding, that is going to be that static friction force that you must apply to overcome static friction. So we're going to use that in the equation. Now the normal force is the perpendicular support force. That's basically the force that the tables are providing on this wooden block to keep it from falling down to the center of the earth. So the normal force is just going to be the weight. It's just going to be in the opposite direction though. And remember, for this lab, we're only using magnitude. We're not talking about directions. We're not doing positives and negatives. So whatever the weight that I found in this lab, gravity pulling down on this box and this mass, my normal force is going to match it going up because it is a level surface. If it was on an incline, it would be different, but because we're on a flat level surface, it's going to be the same. Now, friction is dependent on two things: the nature and condition of the surfaces and how hard those surfaces are pressed together. So if we look at this equation for static friction, that lowercase Greek letter mu is the coefficient of static friction. That's the nature and condition of surfaces. That's basically what the surfaces are made out of and how slippery they are. It's a ratio. It doesn't have a unit. It's basically saying how much of the weight of this object would I have to apply to get it to start to move. And the normal force is how hard the surfaces are pressed together. So using this equation, we can calculate the coefficient of static friction for this condition. Now we can do the same thing for kinetic friction. So once again, the normal force is how hard those surfaces are pressed together. Now the coefficient for kinetic friction should be less than the coefficient for static friction. The idea behind this, if we look at the graph for friction, it's always going to require more of a force to start that object sliding than it does to keep that object sliding. There are some exceptions, like with Teflon, where they're the same. For most cases, the coefficient for kinetic friction is going to be lower than the coefficient of static friction. So what we're going to do is we're going to use this equation, except for this time, what we're going to do is for the force of kinetic friction, that is the force that you are applying as it's sliding at a constant velocity across the table. And that force should be lower than the force required to start that object sliding. Now looking at these equations for friction, friction only depends on two things. Number one, the nature and condition of surfaces and how hard those surfaces are pressed together. So using that information, I like to conduct some different thought experiments. So the first thought experiment I like to do is, what would happen to the results of this lab is if I did the lab where the box is vertically, right? So I still have the same weight pulling down, right? I still have that, right? It's still the same weight, same mass, same wooden box, except what I've done is I've reduced the surface area touching the table. What would happen to my results? Now the next thought experiment is, what would happen if I did the exact same experiment, except this time I spread a bunch of dish soap all over the table, making the surfaces slippery? What would happen to my results? The next thought experiment I do is, what happens if I did the exact same experiment the same way, except instead of using this 500 gram mass, I put a 1 kilogram mass in here instead. What would happen to my results? How does this affect the frictional forces? And the last thought experiment I like to do is, what would happen if I did this exact same experiment, except I did it on the moon? How would this affect my results? How would this affect the different variables of this lab? So once again, this is the friction lab.